Hello everyone, I hope you are staying healthy and adjusting well to this strange situation we find ourselves in. This module is M4.4, Total Internal Reflection. In the last few modules, we have been talking about bending light through reflection and refraction. In most cases, light is both reflected and refracted. The intensity of the reflected and refracted light depends on the angle of incidence. The PhET simulation called bending light depicts the relative intensity of reflected and refracted light by shading the rays. So you can see in this diagram that the refracted ray is darker, indicating that in this particular case, most of the light incident on the surface is refracted into the second medium. Steeper angles of incidence, that is, angles that are closer to 0 degrees from the normal line, refract more light, leaving a smaller percentage of light that is reflected. Shallower angles of incidence, closer to 90 degrees from the normal line, reflect more light, leaving a smaller percentage of light that is refracted. Another feature you may have noticed in previous modules is that the direction of the bend in the refracted light depends on whether the index of refraction of the incident medium is greater or less than the index of refraction of the refracting medium. The picture on the left of this slide shows a ray produced in air with an index of refraction n equals 1. This ray then travels into glass with an index of refraction of n equals 1.5. Since the index of refraction in air is less than the index of refraction in glass, the refracted ray bends towards the normal line. On the right, the ray is produced in glass with index of refraction n equals 1.5. The ray then travels into air with an index of refraction of n equals 1. Since the index of refraction of glass is greater than the index of refraction of air, the refracted ray bends towards the boundary between the two media. In both cases, as the angle of incidence is increased, the angle of refraction also increases. As the angle of incidence approaches 40 degrees, the angle of refraction on the right gets closer and closer to 90 degrees. You can also see from the shading of the rays in the diagram on the right that as the angle of refraction approaches 90 degrees, most of the light is reflected. Notice that the angle of incidence is 41.8 degrees, and the angle of refraction on the right, where n1 is greater than n2, is 87.9 degrees. At some critical angle, the angle of refraction for the case where n1 is greater than n2 reaches 90 degrees. Here, the angle of incidence has been slightly increased to 42 degrees. The refracted ray on the right has disappeared. This is because the angle of refraction would have exceeded 90 degrees, so the ray does not refract at all. Instead, 100% of the ray is reflected. You can go to the PhET simulation bending light to experiment with this yourself if you want. Notice that this is not a problem for the ray in the left diagram, where n2 is greater than n1, because the incident light will reach the 90-degree limit long before the refracted light does. We can use Snell's law to see why this is happening from a mathematical point of view, and to determine the exact angle where the refracted light got cut off. A ray cannot refract more than 90 degrees from the normal, so let's set the angle of refraction, or θ2, to 90 degrees. We can then solve for θ1 to find the largest possible value of θ1 at which refraction can still occur. Let's start by plugging our values into Snell's law. We notice that sine of 90 is just equal to 1. We do a little bit of algebra so that we can get sine of θ1 onto one side of the equation all by itself. And then we take the arcsine, or the inverse sine, of 1 over 1.5. Our final answer is that θ1 is equal to 41.81 degrees when the angle of refraction hits 90 degrees. Any angle of incidence greater than 41.81 degrees will result in no refraction. This agrees with what we found experimentally just by looking at the PhET simulation, where we found that the angle at which refraction is cut off is somewhere between 41.8 degrees and 42 degrees. This cutoff angle, 41.81 degrees, is called the critical angle. Notice that the critical angle is always an angle of incidence because it is the angle of incidence at which the angle of refraction is equal to 90 degrees. This critical angle at which 100% of the incident light is reflected is usually written theta sub c, and the total reflection of light that results is called total internal reflection. This name comes from the fact that light can be trapped inside an object with a high enough index of refraction, where the light will bounce around internally until it hits a boundary with a sufficiently small angle of incidence to finally escape. Again, total internal reflection simply does not occur if N1 is less than N2. Visually, we can see that when N1 is less than N2, the angle of refraction bends towards the normal line, so the angle of incidence reaches the 90-degree limit long before the angle of refraction does. A very important application of total internal reflection is fiber optic technology. Information can be carried by light down a flexible thread or fiber made of some material with a high index of refraction. This material is then coated in another material with a very low index of refraction, ensuring that everywhere along the fiber, N1 is greater than N2. Light can then be shown into one end of the fiber, and it will travel all the way down the fiber, internally reflecting the whole way. Fiber optic technology can even be used to transmit an entire image through a thin cable. There are many medical uses for fiber optics because this technology allows medical professionals to actually see images of the inside of a person's body without having to make invasive cuts or do invasive procedures. In the last module, we noted that reflection, refraction, and dispersion all contributed to the optical beauty of a diamond due to its high index of refraction. But the real sparkle of a diamond occurs due to total internal reflection within the gem. Let's calculate the critical angle for diamond. We find that the critical angle for diamond is 24.41 degrees. That is a pretty steep angle. That means that once light goes into a diamond, it can only exit if it is 24.42 degrees or less from the normal of each surface. This is practically perpendicular to the boundary. Most of the light that goes into a diamond, therefore, bounces around several times inside the diamond before actually escaping. Total internal reflection is also used to keep people safe on a daily basis. When illuminated by a car's headlights, safety reflectors, like the ones on bicycles, appear as bright as a flashlight, but they don't require a battery. They simply recycle the light that hits them several times over through total internal reflection. In summary, when the angle of incidence is greater than the angle of refraction, there is a critical angle at which 100% of light reflects because none can refract. This is called total internal reflection. There is only a critical angle if the index of refraction of the incident medium is greater than the index of refraction of the refracted medium. The critical angle is always an angle of incidence. And finally, total internal reflection has a wide variety of applications, from communications to medical devices to everyday safety.